This is Fundamental Problem 10 from Chapter 13. The sports car is traveling along a 30-degree banked road having a radius of curvature of 500 feet. If the coefficient of static friction between the tires and the road is 0.2, determine the maximum safe speed so no slipping occurs. Neglect the size of the car. So we are in the normal and tangential section. So the first thing that we want to do is identify the normal direction and the tangential direction. So the tangential direction is easy because that's the direction that the object is moving in. So that would be out of the page for the car. And the normal direction is in towards the center of the circle. So I'm not going to draw the tangential direction, but this is the normal direction. And the binormal direction is perpendicular to the tangential direction and the normal direction. So that would be either up out of the page or down into the page. And there's a diagram in the book which we can use to determine which of those two directions it is in. So this is on page 58. This is in chapter 12 and it's section 7. So we have here the normal direction and the tangential direction and the binormal direction, and we are told that the relation between them is the unit vector which points in the tangential direction crossed with the unit vector that points in the normal direction gives us the unit vector pointing in the binormal direction. So if we do tangential crossed with normal, we get binormal. So for us, tangential is coming out of the page and normal is going this way, so binormal is going downwards. But actually, if you say it's going upward, it's not going to affect your answer at all. Okay, so we have identified the normal direction and the tangential direction, and now we're going to use Newton's second law with normal and tangential components. So remember I said earlier that I have to use two of these three equations for a two-dimensional problem. So maybe I should figure out what the forces are first. So here we have the car, and we have the normal direction, and we have the binormal direction. I know I have a force of gravity acting downwards. Let's just call this m times g. I have a normal force, which is coming from the surface, exerting a force on the car. It's perpendicular to the surface of contact. So that's like this. And I know that this angle is 30 degrees. So if that angle is 30 degrees, then this angle is 30 degrees, which means that that angle is 30 degrees. The road not only exerts a normal force, it also exerts a force of static friction, and we have to determine the direction for the force of static friction. The direction for the force of static friction depends on the speed of the car. So if the car was not moving at all, and if there was no friction, the car would slide down the incline. So if v is equal to 0, the force of static friction would be pointing up the incline to keep the car from sliding down. However, if we're looking at the maximum possible speed at which the car can go without slipping, in that case, the force of static friction is going to be pointing down the incline, because if the car was going any faster, it would actually slip up the incline. So this is the force of static friction, and because we're looking for its maximum speed, that force is going to be at its maximum value, which we like to see, because if the force of static friction is at its maximum value, then we can use the equation, which is similar to this one, for the force of kinetic friction. We take the coefficient of kinetic friction and multiply that by the normal force. If the force of static friction is not at its maximum value, we can't calculate the force of static friction with an equation like this. We have to figure it out what the force of static friction is in that case from using Newton's second law. Okay, so now that I have figured out my forces, I can see that I have a force pointing in the binormal direction, and I have components of forces pointing in the normal direction, which means I don't have to look in the tangential direction since I don't have any forces pointing in the tangential direction. So I'm going to say the sum of forces in the normal direction is equal to the mass times the acceleration in the normal direction, and the sum of the forces in the binormal direction is equal to 0. This equation, I don't have to do anything else with it right now, but for the sum of the forces in the normal direction, I want to replace the acceleration in the normal direction with v squared over rho. So this is equal to the mass times v squared over rho. Okay, because we have already identified the normal direction and the binormal direction, and we're going to use these equations for Newton's second law, we can see that we have to break the normal force down into components and the force of static friction down into components. Now, if this angle is 30 and this angle is 30, this is a right angle, this is a right angle, so this is 90 minus 30, and this angle is 30 degrees also. So I'm going to draw the free body diagram once again with all of the forces broken down into components. So this component of the normal force is n cosine 30 degrees, and this component is n sine 30 degrees. Then I have a component for the force of static friction. It is at its maximum value, but well, I'm not going to bother writing that. I'll just know that it is. Okay, so this is cosine of 30 degrees, and this is sine of 30 degrees. And now let's start off looking at the binormal direction. That means because the sum of the forces in the binormal direction is 0, I have n cosine 30 degrees is equal to mg plus FSF sine 30 degrees. I know the force of static friction is at its maximum value, so it's equal to the coefficient of static friction times the normal force. So I can say n cosine 30 degrees is equal to mg plus coefficient of static friction times n times sine of 30 degrees. And let's bring this term over to the other side and pull out an n. So we have n cosine 30 degrees minus coefficient of static friction times sine of 30 degrees, and that is equal to mg. Okay, now we can look at the sum of the forces in the normal direction. That's equal to the mass times v squared over rho. In the normal direction, pointing in the positive normal direction, I have the force of static friction times the cosine of 30 degrees, but let's replace that with the coefficient times the normal force. And then I have the normal force times sine of 30 degrees, and that is equal to mv squared over rho. I'm looking for v. I know rho. I do not know the mass of the car. So let's see what we can do here. So I don't know what the normal force is, but I can take this equation and solve it for the normal force. So I have n is equal to mg over cosine of 30 degrees minus the coefficient of static friction times sine of 30 degrees. And then I can take this and I can put it in here. I can also pull the n out, and that leaves me with a coefficient of static friction times cosine of 30 degrees plus sine of 30 degrees. This is times n, but n is equal to mg over cosine of 30 degrees minus coefficient of static friction times sine of 30 degrees. And that is equal to mv squared over rho. And now we can see that we have mass on both sides of the equation, so that cancels out. So to find v, which is the maximum speed because we use the maximum value for the force of static friction, I can multiply both sides by rho and then take the square root. So v is equal to the square root of rho times g, coefficient of static friction times cosine of 30 degrees plus sine of 30 degrees divided by cosine of 30 degrees minus coefficient of static friction times sine of 30 degrees. And then I can plug in the coefficient of static friction, which is 0.2, and I can plug in rho, which is 500 feet, and g is 32 feet per second squared. And I will let you have the fun of plugging that in on your own, but you should get for that 119 feet per second for the maximum speed.